In this second video, we'll be looking at where this frequency-dependent behaviour of op-amps comes from. And in particular, looking at a model of the op-amp in terms of a dependent source. As the slide says, just about every voltage or current source that we've come across so far is what we call an independent source. It has a fixed value, and that value doesn't change. However, there are also things called dependent sources, and these are voltage or current sources whose value is dependent on the current or voltage somewhere else in a network. You can think of an amplifier as a simple voltage-dependent voltage source. Its output voltage is a function of its input voltage, usually just a fixed constant called the gain times its input voltage. To illustrate the idea, have a look at this next circuit. What would the voltmeter read? Notice that we have a voltage-dependent voltage source in the middle of this circuit, whose output is 8 times the voltage measured across the two terminals at its input. So what would the output read? Pause the video here if you need a bit more time to think. Well, the answer is 2 volts. 2 volts because the first thing we've got in this circuit here is a potential divider. And it's a potential divider where both of the resistors are the same. They're both 1K. So, that means this potential divider will effectively halve the input voltage, which is 1 volt. That puts the voltage at this point in the circuit as half a volt, or 500 millivolts. That is the voltage which affects the output of the dependent source. The dependent source is measuring the voltage between this point here and ground in this case, so it's going to be measuring 500 millivolts. It then multiplies that by 8 and puts that corresponding voltage on the output. Well, 8 times 500 millivolts is 4 volts. So this voltage-dependent source here is going to be outputting 4 volts there. This 4 volts then goes into another potential divider. This potential divider also divides by 2, and that results in the output voltage at this point in the circuit here being 2 volts. We can think of op-amps as voltage-dependent voltage sources as well. This would be a simple model of an ideal op-amp as a dependent voltage source. Its output voltage is the open loop gain, A, times VD, where VD is the difference between the voltages at the non-inverting input and the inverting input here. And that produces a circuit which gives you the output voltage is A times the difference between the two input voltages, and that's exactly what an op-amp does. And when A, the open loop gain, can be assumed to be practically infinite, this gives you a good model of an ideal op-amp. But it's not a very good model of a real op-amp, because real op-amps have an open loop gain which is a function of frequency. A much better model of an op-amp, which reflects some of the components inside the op-amp, is this one. It's a bit more complicated. It has 2 dependent sources. The first dependent source here is a current source. And that current source, IB, has a value given by a constant B times VD, the difference between the voltage at the non-inverting input and the voltage at the inverting input. So IB we can write as B times VD. IB is now driving into a parallel combination of a capacitor and a resistor. So that generates a voltage across the resistor given by the current flowing times the impedance that the current is flowing through. The impedance the current is flowing through is the parallel combination of this resistor and this capacitor. So again, using the complex impedances, that would give me R over j omega c divided by R plus 1 over j omega c. That's just the standard formula for two impedances in parallel again. The product of the impedances divided by the sum of the impedances. This can be simplified by multiplying top and bottom by j omega c, and that just gives me IB times R over 1 plus j omega RC. There's then a further voltage-dependent voltage source which produces the output voltage, and its value is equal to the voltage that appears across the resistor. That just gives us Vout equals to VR. Put all of this together and we end up with the output voltage is VR, which is IB times R over 1 plus j omega RC, and IB is B times VD from up here. So that gives me VD times BR over 1 plus j omega RC. So effectively, my open loop gain, the ratio of the output voltage to VD, the difference between the input voltages, is BR over 1 plus j omega RC. Now, at DC, when omega is 0, this is equal to just BR. It would be BR over 1 plus 0. So I will usually write this in terms of the open loop gain at DC as ADC over 1 plus j omega RC. And I could even go one step further and write this as ADC, the open loop gain at DC, divided by 1 plus j omega over omega B, a characteristic frequency of the op-amp. And if I wanted to write this in hertz, I could just divide the omega and the omega B by 2 pi, and that would give me the open loop gain of my op-amp is ADC divided by 1 plus j f, the frequency in hertz, divided by FB, a characteristic frequency of the op-amp. And as we've just seen, FB is actually the 3 dB bandwidth of the open loop gain. If we were going to plot the open loop gain against frequency, FB would be the frequency at which that open loop gain has dropped by 3 dB from its low frequency value. Next time, we'll have a quick look at the difference between open loop gain and closed loop gain, and have a look at the characteristics of a real op-amp.